Thank you so much for the introduction, and thank you so much for the invitation for allowing me to speak here. So as in the introduction, so like currently I own like a node on Koa, and I have been really taking advantage of like also like the community node. And so today I'm going to talk to you a little bit about my research, which is soft material design with HPC. And because this is a lightning talk, so I'm literally going to spend most time trying to tell you what are soft materials and like the high level things of what we do. And at the end, I'm going to like do like a little snippet of like what two of my students are doing. Okay. So we're the programmable soft materials research group, and then like you can also like shorthand it to be called Matter. Like it took me a long time to come up with this name, but so I'm the PI, and then right now I have like one PhD student, Gregory, and then another one in common session, and one master student, like 2 undergrads and 2 high school students, and they're all working on different kinds of like computational material stuff. And then there's like 2 different material platforms that my group have been doing right now. So one is called magnetic tension materials. For the interest of the time, I'm not going to talk about it, but if you're curious, like why it's called magnetic tension materials, like what do they do, come talk to me. I have like I have toys, and you can look at them. And the other thing is like this model system called Petri particles. And then I will talk a bit more about like what they are and why we're interested in them. And so today I'm going to like highlight research that done on Petri particles, like specifically 2 different projects by my PhD student Gregory and my undergrad Carl, where Carl is sitting here. Okay, so before I go into what exactly I do, this is a very diverse crowd, so I just feel like I need to first introduce what are soft materials. And so soft materials is literally ubiquitous, like it's all around us. And then it also kind of like counterintuitive in the sense that soft material doesn't mean the things have to be soft. So people can argue that wood, like or like the tabletop right now, can be like a type of soft materials. But and it is really hard to have like a very uniform definition for what soft materials are. So I'm going to show you a bunch of examples. So hopefully that you can then do induction yourself to think, okay, what are soft materials? So first class, liquids are definitely soft materials. So water, like very interesting material, and because like water actually has fascinating properties, as like the highest density of water happens at like 4 Celsius instead of like when it gets to like lower. And then also like the freezing behavior of like water is also very interesting. So that's one thing like people who study soft materials study a lot. And if you're curious, there's literally like a whole like article on like the war on water, where literally like 2 groups doing like computational research on like super cool water, and they keep getting different results. So it's like a fascinating piece, and also very related to like how you do simulation on supercomputers and how you prep your simulations. Okay, so colloids are also soft materials. So what are colloids? Like one thing of colloids is like, so we all have paint in this room. So paint is a type of colloid solutions, and then like milk is also like a colloid suspension. And then people really like to use like the particles to think about a lot of like assembly behaviors. And foam are also soft materials, and then foam also has a property that you can have a rigid foam and a non-rigid foam. And to study that transition, so there's also a lot of interesting science to do with that. So there's also granular materials, so sand. Sand also has like this very interesting property is like when you're trying to pour sand into like a castle, and at some point it's going to have an avalanche. And you can actually predict the angle of like when that avalanche can happen. And then liquid crystals, so also type of soft material, very important. This is why we have all our computer displays right now. And then this list can keep going on and on. So we can gel, very important, like we use it every day in our shampoos and stuff. Polymers, biological materials are all soft. So you can have your DNAs, proteins, and so on. And so hopefully I've already convinced you why do we care about soft materials, but I'm just going to put on a few more examples. So liquid crystal displays, and then like photonic crystals. So this like is very interesting, where the color of these butterfly wings, that they have all this color, not because there is some kind of like pigment there. Those colors exist because of the underlying structures of those like wing materials. And if you change the structure, they will have like different colors. And so this is like a very physical behavior, not a chemical one. And this is also something I really like to talk about. So glass is also a type of soft materials, and glass is not really a solid. It's like actually just like amorphous liquid. And then there is also sometimes glass will just like catastrophically fail, and there's a whole collaboration trying to study why glass does that, and can we predict that and prevent that. And then to something else that there's also like 3D printing needs. So here there's like really a lot of different soft materials research going into that. So first you need to really think about the rheology of designing how you're printing the meat so you can print it evenly. And then you also need to care about the structure of the meat you're printed, because like now we all can make synthetic meat very well for like ground meat, but like making a steak is still hard. So like you really need to think about where do you place the fat and the muscle to have like a synthetic steak that has like the right texture. Yeah, and there's more. Okay, so this is kind of like an overview of like what are soft materials and what can soft materials do. And so now I'm going to talk about like the thing I really focus on. So like the thing I think about is like self-assembly. So what does self-assembly mean? That here I'm going to show you my favorite movie is from Big Hero 6. So here you can see that we have all this like tiny microbots, and then collectively they can assemble into a structure, and then they can reconfigure into a different structure and then perform a function. So every single building block here is simple, but by collectively you can call that collective intelligence, or like something like or emergent behaviors that they can perform something together. And so this is kind of like the research I think about is like I think about what kind of building block we need to assemble into a structure, and then or if we need a particular structure, what kind of building block we need to achieve that. So as I said, like we want to understand the relationship between building blocks and assembled structures, and we also want to design building blocks for target material structures and properties. Yeah, so the thing I'm going to talk about, like the current research using Koa is this like patchy particle assembly and design. So patchy particles are particles like there's like a bunch of them here. So it's a model system that kind of like you have, sometimes you have like a box sphere or some other shapes as to serve as a body of your particle. And then you have like can have this like little tiny patches on top of it to indicate some kind of interaction site. Or you can have this like hemisphere here that is just like built on top a bunch of small particles. So the reason we care about patchy particles is like this is like kind of like a generalized model that is general enough but also specific enough that you can imagine if you want to study like a given protein or some other building blocks, that you can use this kind of like coarse-grained model to model those behaviors. So, and this is kind of like the space I like to live in. It's like it's general enough, but then we can also specific enough that we can draw connection to like a real material system. And so there's like kind of two projects we're doing at the moment. So the first one is inverse design with JAXMD, and I will talk about what JAXMD is later. So the idea here is like if we want to assemble like a structure, what building blocks we have. And the other one is like for design with foam glue and other molecular dynamics engine. The thing is like, okay, so this is the same we have. Like if you throw a lot of them in a box, like what will you assemble? So inverse design with JAXMD. So JAXMD is like this new molecular dynamics engine that is end-to-end differentiable. So kind of like we can just like route the simulation into a function, and then you can take gradients of that and have it to do like optimization and to figure out what is the best building block with some kind of loss function. So this is kind of like the design loop. And yeah, so and then kind of one thing to point here is like this is like a very expensive like calculation. That's why like I needed to get like a H100 NVIDIA GPU to do everything. And so I think I'm probably like really short on time, so I will go through this very fast. Yeah, so kind of like our goal was like try to find out what is the best building block to assemble this finite squares. And so here are some results. And then kind of like we were doing an optimization of 300 steps. And then I think the total optimization took around like 24 hours on H100 GPU on Koa. So, and the other thing is like what we're doing is like what Carl is doing here is like pattern hemisphere assembly. So the idea here is like we have this building block, and this is kind of the interaction where the green particles attract each other, and everything else are just like a steric interaction. And you can imagine having like different realization of this hemisphere, that you can have like a bigger patch or a smaller patch, or you can even have a patch on the bottom. Yeah, and this is like not coming out of nowhere. Is we have a collaborator that they can actually make this kind of building blocks, and they're like, we don't really understand how they assemble into or what they're good for. Can you help us? And so here is kind of like showing a realization of like the simulation Carl has run using HomeDeepBlue. And so HomeDeepBlue is another MD engine that is like super accelerated on both CPUs and GPUs. And you can already see that there are some kind of clusters forming where the grains are attracting each other. Okay, so that's the end of it. That I just want to highlight. These are like the two different molecular dynamics engines I use on Koa, both open source, Python based. And here are other analysis and data management softwares I use to help me do the work. I especially like Synapse is like very, very useful. And if you have like large parameter space you need to go through, and you want to find a better way to organize your data, come talk to me. Like I really like Synapse.
You're not there, okay, so whatever. So, yeah, my research group is called the Cosmic Ray Antimatter group. And so what we do is we study cosmic rays. And cosmic rays are similar to the light that you see from stars, but they're also different because they have a charge. There's something like a proton or an electron coming from some sort of astrophysical source, and then they reach us. And one of the interesting things that we can study, it's not moving, okay. So, maybe we have to share, I think that you might have to share, we have to share something different. Okay, so and one of the key motivations is that we would like to understand the nature of dark matter. So dark matter is this interesting quantity that we know that it exists. It's 5 times more abundant than what we're all made of, like including planets and ourselves and stars and stuff. But there's more out there that doesn't shine. So that's why physicists who are not as good as the folks at branding just call it dark matter. We don't understand it, so it's dark matter. All right. Okay, it seems to be working now. Excellent, thank you. Sorry for not bringing my own computer. So, okay, so we use cosmic rays as messengers from the galaxy to tell us something about the galaxy. That's a short story. We're trying to find something that we know exists, but it's like one of the biggest questions in physics, known for 100 years, and we don't know what it is. So we study cosmic rays, and that's kind of a tricky business. So you follow cosmic rays from their origin source on their trajectories through our galaxy, into our solar system, into our atmosphere until they meet, for example, a detector at balloon altitudes, which is about 4 times of airplane altitudes, or something that on, let's say, in space, like at satellite altitudes at a couple hundred kilometers. Okay, now I am involved in 3 different experimental efforts. So by training, I'm an experimental physicist, like this co-driver behind not only like computer programming. So what I'm working on is it's one experiment that is mounted on the International Space Station that has been installed in 2011, and we're still analyzing the data. Then we just built a new experiment, a photo of an updated thing, which we're going to fly from Antarctica. And then I also work on experiments that are actually on the ground to supplement the measurements that we do in space actually for the interpretation. And everything that is related to particle physics means you have like lots of statistics, lots of data coming in, so that you need data science techniques to analyze all of this data. And particle physics, for like I think like many of the early adopters on even developing the modern data science tools. Okay, so I started working with the HPC in 2015, and I was still relatively new at UH. So we did big studies of like how particles behave in the geomagnetic field. So it's making these complex loops here. And we had our biggest study yet was the production of, or the simulation of the creation of anti-helium, which is really hard to make in our galaxy. There are maybe hints that anti-helium has been detected in our galaxy, which is completely unforeseen, which could be another hint of some sort related to dark matter, but you really don't know what it is. And at that time, it took like thousands of compute time years to get this done. And like I think the largest contribution of this calculation was done here by my grad student, our postdoc, Antimatter. And so some part was also done on OSG. So that was really interesting that we could simulate at that point. That was the first time that this could be done. We were like a bit silent on the cluster over the last 2 years because we built a new experiment, which is this thing here. And we were, this is an experiment to detect antimatter in space. It has kind of a complicated signature in how we say it's antimatter, not something else, requiring lots of simulations, but we had to build the experiment first. So this is the launch team in Antarctica. I was also there, not on this picture. Unfortunately, we couldn't start in December 24 because the weather was bad, so we have to go back and try it again. But the data of this thing will trigger lots of additional new work on the cluster here, which has like a big impact on the whole international collaboration. So this project is led by Columbia University. We have collaborated with UCLA, Berkeley, Northeastern, INFN, and JAXA, which is the Japanese space agency, and INFN is the Italian Nuclear Institute, I guess, something. So it's like a gigantic help, and I really want to say thank you for all the hard work here by the people from the HPC team with different names over the years, Chrisy, Koa, Mānoa, and so yeah, it's really helpful for my team, and I'm looking forward to doing more work on the cluster. Thank you.
V-VIS Spectra just introduced about my lab since I just joined in last fall. So mainly my work is for the development using quantum mechanics and try to expand it for the very large scale computation. And because I am a developer, so it might be sounds like I try to make an application all over the place, but mainly when I try to develop the method, it's not focused for the one that only work for one particular problem, but try to make it broad enough for the different types of the problem, especially in chemistry. And since it's also involved in terms of the software development, using quantum mechanics that use a lot of the computer resources in terms of disk and memory, that's why I also involved in terms of have some work that close with the computer science part. For example, try to port the code to the GPUs, and this is one of the example that try to port the QM code to the GPUs and let it run on the DOE supercomputer. So this is the example that we try. This is the first time that we can use the quantum mechanics running on more than 1,000 number of nodes. And this is the result that I run on Aurora, which is now is like the third the rank 3 from the top 500 supercomputers. Also, like because as a developer, I also another application is also on the prediction of the binding free energy, which involved in terms of for the drug design. For today's talk, it's my current research that I working using Koa facilities, and this is the collaboration with Professor Ralph Kaiser. So basically, once I joined to the UH, then Ralph Kaiser stopped by and asking me, he had some problem from the experimental that he detect the UV spectra for the PAH or the polyaromatic hydrocarbons. But the thing is, his spectra is different. It's not look the same as the free molecule of those PAH. And as the spectra is like you could see here, this is the spectra. It's very difficult to elucidate. So then he come and asked me, can you help to use the quantum chemistry to solve this kind of problem? That's bring the goal of this work. So try to elucidate or predict the UV spectra of the PAH, and also Professor Kaiser hypothesized that the difference of the UV spectra is probably because the PAH interact with the surface. That's why it makes the spectra look different. So then in this work, I will try to do the simulation for the free PAH and also compare it when it interacts on the graphene surface, which is more often kind of expected to happen on the space. So on top, that's the free PAH. So first I try with the different linear PAH by increasing the benzene ring from n equal to 2 to up to 6. And then after that, because as I mentioned, would like to study if once I have the aromatic rings interact with the graphene, how it's gonna change in terms of the UV spectra. But because graphene is too large for the calculation, and it might not fit to the computer resources, so I have to reduce the size. So one, the smallest that I think is kind of close to graphene, so I use the opaline to represent graphene. And then after that, have to think, okay, now I'm gonna have the PAH interact with the opaline. The question would be how they're gonna interact with each other. That's why you could see here there are different configurations. For example, if I have only the naphthalene react with each other, it could form like a sandwich, or I call as a stack, or it could form called like a T-shape. And as a T-shape, it could be like two form of the T-shape. And that is the same thing once I move, instead of using the naphthalene dimer, then with the naphthalene and opaline dimer. And so based on the calculation using the DFT, this is the predicted spectra for the different linear PAH. And if I look at the data closely and collect the lambda max, which is the wavelength that provide the highest peak. And we can see there's a linear relationship. The lambda max will increase as the number of the ring increase. Then after I kind of understand and see that okay, the computation is reliable for the free PAH, then it's time to study for the complex. So this is first, instead of jump from the very small system to the very complex system, I first do the comparison for the naphthalene dimer. And you could see the spectra using a different naphthalene dimer configurations. The spectra look differently, and at the lambda max, they also located in the different places compared to naphthalene monomer. And if I look at it closely, for each of them, for each of the dimer, I could see that, okay, the character of such transition is due to, for example, for the stack, then it's showing that there's a strong interaction, there's an MO overlap between the two monomers. And then with the T-shape, we can also see some like interaction between the two naphthalenes. But I would say the interaction is less than the stack. And that's for the small, for the naphthalene dimer. Then for the naphthalene overlene, I also have to do the calculation for the overlene to first see how the spectra is look like before it's gonna form like a complex with naphthalene. And this is just to show the orbitals as the free molecule. Once I do the calculation for each of the complex at the different configurations, well, the spectra look quite similar. The number of the lambda max are very close, so it could be either there's some change or some interactions or some like numerical instability. So that's then I later looking at the orbitals and everything. So in the end, it looks like there is no interaction. By looking at the orbitals on the right here, there is no interaction between the naphthalene and the overlene. So basically, those different numbers, it's just the numerical instability, pretty much all of the transition is from the dimer, it's mainly from the overlene. And so that's all of the results that I have so far. But because, as I mentioned, graphene is huge, but I choose the very small model to represent graphene. The next step that I have to do is to expand my toy model to represent the graphene sheet like bigger to see if there's going to be any interactions between the pH and the naphthalene, and also like if I try that and confidence enough that the result is consistent, it could be the case that the UV spectra from the experiment might not be due to the interaction between the naphthalene or the pH with graphene. Because in the interstellar, it could be the surface can also be the silicon. That could be another surface for me to test. Thank you.
Specific. And why it has to do with potentially our rural areas not taking advantage of the mammography services we do have. So one of our projects is called Makabalu. It's an accessible point-of-care ultrasound for the rural Pacific. And this is where you take these very inexpensive portable point-of-care ultrasound systems and bring it with you in a backpack to the community and do early detection and screening in that way. But since training is very limited for those that can do this type of work, we are preparing these devices with an AI algorithm that will increase the specificity of the device because ultrasound in its current form is not used for screening because of its high rate of false positives, generally 2 or 3 times higher biopsy rates than mammography. So this project is to pair the AI to try to give it better specificity and reduce that false positive rate. One of the projects within our group that's been very successful so far is the AI algorithm itself, trained on thousands of images that we have from our partnership with the clinical facilities in Hawaii. And this is the work of Ariana Funnel, where she's developing a clinically relevant concept bottleneck model for detecting breast lesions that we're using in ultrasound. And the idea of the model is that it is trained to predict a lexicon that the radiologists and care providers are used to working with and identifying as suspicious. And then further predicting the probability of malignancy from that lexicon. She has a clever design in that it allows the user to interact with the lexicon predictions so that if they disagree, they can flip a predicted value, and the model will update based on the input from the user. Lastly, she left in an open channel that didn't use the concepts and was successful in showing that the concepts were, in general, capturing most of the detection information without leaving information behind and not being used. And here's just an example of how her algorithm predicts the lesion with a delineation and predicts the lexicon values down below, and successfully provides a malignant or benign diagnosis. If we go further in her work, she's also developed a breast density measurement. Breast density is the strongest risk factor for who will develop breast cancer other than age. And if you don't, it's measured through mammography. So if you don't have mammography and you're using exclusively ultrasound, it would be beneficial to have a breast density measurement from ultrasound to include in these comprehensive risk models. And she's done that and showed that she has very high accuracy, especially in the categories of highest and lowest risk, and that she's plugged that into existing models that use the mammography breast density and showed that it remained accurate. And this was just recently accepted for publication. Lastly, part of the resources we use for our machine learning projects is something I began when I came to Hawaii called the Hawaii Pacific Island Mammography Registry. And this is a collection or curation of all the breast imaging, including MRI, mammography, and breast ultrasound from about 4 clinical centers. Currently, we have curated about 125,000 women with over 568,000 total imaging visits, and the total size of that data set, I think, is sitting somewhere around 80 or 90 terabytes with 67 million DICOMs. So we also outline all the different combinations of tumors with these imaging technologies, so we can hopefully solicit others to use this data with us and learn more about the risk in our women. Another study that we've done a lot of work in our machine learning efforts is the shape-up cohort. We've recruited 800 adults, 400 children, and then 360 young children across 5 ethnicities and both sexes and across different BMIs. This is used to look at the optical shape of the body, or the body shape as you measure with a 3D optical system, and infer health information from that. And just as an example, here's a little infant this little infant, of course, is much too young to stand, but we can repose the body into a standardized positioning, even though they were scanned laying on their back and while they were moving, actually, because the scanning technology we're using can take a scan in 10 milliseconds. So in this way, we can standardize body shape and dimensions, as well as look at more complex models using the mesh points themselves as inputs to the model. And this is just an example of how we can take a scan of a young child and extrapolate out that what is their likely life course if we aged them from a young age of 7 to something like 18 years old. And there's examples for a boy and a girl here. And this is driven from our models. Within the cluster itself, Nick Laser, another student that I'm working with, has done all-cause mortality predictions from an imaging mode called DXA, and that's an X-ray technique that looks at the whole body. And what he showed is that using these DXA images with all the clinical information and looking at the visits serially over time gives the very best prediction of mortality from the imaging. So I think this would rival any other method of figuring out all-cause fatality in a large population. We've also done some variational autoencoder work, which includes trying to learn what the DEXA image looks like. And you can see here the AI, the VAE learning what the DEXA image is, and it slowly, as it goes through its epochs, is gaining information on exactly what it's looking at. And this is done by excluding regions randomly and having it guess what the regions are. So this was a very successful project by Lambert Leung that graduated last year. And he was able to break apart the autoencoder and connect up a 3D optical mesh from the same person and predict the DEXA scan that person would have from their 3D optical scan. And really fantastic work and fantastic results, and showing how predictable muscle and fat is from the external body shape. Lastly, I just want to mention that we've started this federated learning consortium with NCI, and we're a part of it with 2 other NCI designated cancer centers to work on problems that no one center can solve on their own. And this is a project that Lydia Solis within ICS has taken on and taken the lead on presenting our models to the other cancer centers. Lastly, we do host workshops like this International Breast Density Workshop, international workshop that we're hosting in Kauai this summer. And this used to be just a breast density meeting, but now it's mainly just an AI meeting. So thanks. I hope that gives you kind of an update and a review of what our group's doing.
Thank you, Coley. We like to combine cyber infrastructure along with cybersecurity and machine learning. So I'll be going over a few of the projects that we're working on currently. We have a few partners that have asked that we don't expose too much, so it might be a little high level, but I'll do some of that. I'll talk about how we use the cyber infrastructure here at UH and Jetstream as well, and then I'll go through some of the experience that we've had with some of the infrastructure itself. So, as I said, we leverage AI and machine learning techniques to solve and automate cyber intelligence. They also develop proof of concepts to then work with federal agencies and private sector partners. And some of these have included DoD, DHS, which we're currently working with, NSF, etc. And while doing that, we also train top-tier cybersecurity professionals and students in offensive and defensive cyber and AI research and development. One more thing I'd like to state with that is that we have a mixed team of postdoc students, undergrad, and cybersecurity professionals. So the 2 main resources that we use are Koa and Jetstream. So for Koa, we mostly use this for training our AI models, specifically LLMs, for detecting things like sensitive information inside of code, and then also running verification processes. This is a very computationally expensive thing to do because there's a lot of context in some of these large-scale projects that we use, and they just can't fit in, on normal consumer hardware. As for Jetstream, this is more of, I would say, our Swiss Army knife of different things. We're constantly using it for prototyping and long-term tasks as well. So running things such as web hosting and persistent LLMs. Just the other day, I was running 2 separate instances where we actually have 2 LLMs trying to attack each other and take each other offline. So there's always different use cases that we're using Jetstream for, and it's definitely very useful for us. As for our experience with Koa, I went around the lab just to see what some of us had to say. The onboarding process with both Ron and David, we found that to be a really useful experience. It's about an hour and a half, but definitely worth it. There's also always very good support from both Sean and David. I feel like within a day or so we get something back if we have issues. So we're very grateful for that. If we ever need to do a very CPU-intensive task, it's normally pretty easy to spin something up and get an instance. However, as Sean had mentioned, there's a lot of people working right now with GPU nodes, so it's a little bit harder to always get those when we need those. We noticed some things inside of the actual GUI interface where we can see that there are GPUs available, and then we select something very simple like any, but sometimes we're not always able to get an exact instance. And then as for Jetstream, we find that the ability to get an instance, as I had spoken, multiple instances working at the same time, we can get GPUs on those as well, which is definitely needed for our work. We don't really have too many downtimes, and they're pretty communicative when there's updates and stuff going out, that there will be some downtimes. And fast downloading, whenever we need to move our large data sets over to different machines, it's pretty easy to do, and there's not much work for that. We do find it to be a little confusing, and this was some issue that we had for a bit, is we had assumed with regions that it was more so specific to our schools, and we didn't know that we could go ahead and actually select anything from our partners. So we were trying to get GPU allocations for a little bit, and we were held up on that. Thankfully, we were able to figure that out. One of the other issues that we've noticed is that we're kind of limited to a single GPU. I believe it's an A100, so about 40 gigabytes of VRAM, and sometimes we have to do a little bit of optimization to train some of these models, and we can't train everything. So that's a little bit of a limitation that we found. And then sometimes instances will crash if we're hitting them too hard, and they're like full-on deadlocked, and we have to reach out to support. I believe that is everything. I don't know if there's any questions. I'd like to keep it nice and short. If not, that's my time. Thank you.
That's great. That's perfect. Hello, thank you, goodbye. So yeah, I've got a lot to talk about, so I'm going to be super brief, because all I'm going to do is talk about a newer project that's happening. So some of you might know I work on the Change Hawaii project, which is about bringing together computer scientists and climate scientists to figure out how to make Hawaii more resilient in the face of climate change. And this project has really taken a life of its own. And this new part of it is what I'm going to talk about, because it's a new award that we just received. And essentially, a big key part of understanding the climate is to have sensors out there so that you can monitor things. In Hawaii, unfortunately, because we're so small relative to all the simulations that the United States generates, we're like a pixel. So there's not a whole lot of data about the climate in Hawaii. And so I started teaming up with a group at Argonne National Lab and Northwestern University. I spent 22 years of my life in Chicago, so that's how I got to know these folks, and then they kind of hunted me down when I moved to Hawaii, and they said, how can we come to Hawaii more often during the winters? But intriguingly, they were working on this pretty awesome sensor called, ironically, the SAGE node. I work on a project called SAGE as well, so there's some confusion there. And this dovetails well with the sensor network that's been built out in Hawaii called the Hawaii Mesonet, which has got a whole bunch of sensors on it that measures everything from rainfall to climate, wind, and so forth. What's unique about the Argonne sensor is that in addition to all the same climate sensors, they also have a GPU on board. And so what they like to do is to investigate the use of AI within the GPUs on board, so that out in the field you can try to detect things that are happening in real time. Because if you think about extreme events like forest fires, like the one that happened in Lahaina, every second counts, right? And so there's no such infrastructure really at large scale in the United States. So these folks have built about 78 nodes in the mainland, and they're expanding out to increase the footprint in the mainland, but also to increase the footprint for Hawaii. We have about 2 to 3 sensors in Hawaii right now. This is considered a NAIR resource. For those who may not be familiar with the term, it's the National AI Resource Initiative funded by the National Science Foundation. So once it's up, it's publicly accessible to all scientists as well as the general public. And I'll speak to how we're going to make it even more accessible to the general public in a moment. But here's an example of putting the node out in Lahaina. We have one at the Board of Water Supply. And we take all that data and we feed it into our visualization system so that you can see the data coming off of it. And this is actually a little video of the node in Lahaina. This part is the Hawaii Mesonet, and it's got a whole bunch of climate sensors. And then above it is the SAGE Waggle node. And you can see it's got cameras pointing up and downwards, infrared cameras. We have full control of these cameras, and it's connected via Starlink. I know Elon Musk is getting a bad rap these days, and sadly, I own a Tesla too. But we do rely on Starlink for this, because when Lahaina burned up, right, all the cell towers died and there was no more communication, and Starlink was the only mechanism for doing so. We also have a similar kind of setup at the Volcano National Park. We happened to have it set up about a year ago, and in June, when the volcano started erupting, our AI that we were testing out said, hey, by the way, there's a volcanic eruption. And I thought, oh, okay, that's interesting. So we went on USGS's website, and it's like, oh shit, it happened. So it was like, you know, we can't fabricate a disaster in order to detect it. Fortunately, we had something happen to allow us to validate our work. And so then we started using that as a means to improve and test out different AI approaches. We're primarily just looking at off-the-shelf, large visual language models. This is stuff that you can ask ChatGPT to do, as well as other AI systems. And we're just trying to see how good are they at detecting things like floods, fire, volcanic eruptions. And these are actually literally prompts that we gave to the visual language models, and they will come back and say, yes, there's a fire and so forth. So what's interesting about this for the general public is that you do not have to know how to write Python codes to access the data from these sensors anymore. In the future, we're going to interface more and more with these large language models so that the general public, decision makers, can ask really high-level questions. And it will go to these sensors, fetch the data, process it, and answer your questions for you. Of course, there are challenges. We have to make it super reliable, right? But I think this is going to be really transformative to the future as we make this kind of capability more accessible to the general public. These are the planned build-outs of the sensors over time. So you see we have 10 for Hawaii, and they're actually interested in giving more to Hawaii because they kind of notice our footprint is too small and they want to expand it, and NSF is really interested in helping us. But we're partnered with a bunch of organizations who are interested in ecological applications, and also San Diego, which does a lot of work in wildfires, and so they're going to bring their expertise to help us here in Hawaii as well. I mentioned all the data. Well, part of it goes to the Hawaii Mesonet, which is supported by Sean, but also we have data going into our software called also SAGE, which stands for the Smart Amplified Group Environment, and it's an environment that runs on walls like this, but also actually on laptops. So even if you didn't have a large display wall, you can use the software. And it allows people to collaborate, throwing up information on the screens, but also bringing in websites that may have streaming data so that you can juxtapose them for decision-making purposes. So here are just the tutorial video showing you how, it's kind of slow here, but you can share information between laptops, large screens, be traveling, or you can have collaborators all around the world looking at all the same data sets. Here's a little post-it note session. You can brainstorm ideas. You can fuse it also with artificial intelligence so that it can summarize post-it notes from discussions. You can also take PDF documents and create syntheses of them in this kind of space. And all this is actually run off servers that we host in Jetstream too. Now, the Lahaina and Volcano stuff is also running off the Jetstream too for OpenAI and Llama to compare against our onboard GPUs. Here's some example of showing people writing Python codes within the environment that allows them to collaborate while they write these Python codes. It's great for classroom situations where you have a bunch of students all working on projects together or hackathons. This This is used for a little data dashboard so that you don't have to code. You bring in your websites that contain all the dashboards and juxtapose them on the screen. If you want to download your own copy, just go to stage3.net and you can just run it on your laptop. And I think that's it. How's that? And we always have to thank our funders. That wasn't a minute, sorry.